Finally. If you're with us today for the first time, be sure to have picked up a copy of the syllabus for our lecture gathering. And if you are enrolled in 46L, a copy of the syllabus for 46 Laboratory. Again, laboratory classes start Monday, a week coming. So be there, ready to go. As we reminded you, if you're not prepared for laboratory by having appropriate attire as well as the laboratory manual, you will not be allowed to enter the laboratory, which means you can't check in, which means you might lose your lab space. We don't want you to do that. And today also, I purposely made available for you an information sheet. The information sheet is two-sided. For each quiz and each exam, you'll receive a copy of this information sheet so that you will have access to the information which it contains. You don't have to memorize this stuff, but you do have to be able to use it. And a lot of what we're going to talk about in class will remind you how you use the information on this sheet. Please, if you will, have this sheet with you for each class gathering, because we will often refer to and put to use the information on this sheet. So for your benefit, for the benefit of our progress, have this thing with you. There are limited content information sheets in the notes, but I decided let's get it all together and put it on one nice sheet so that you can have the whole 9 yards. And now, believing that at this point you each have the class notes, again, abbreviation CN2 for Chem Notes 2, written by me but written for you, so that in class you can spend time paying attention to what we discuss and get at understanding, as opposed to spending time to write notes, because now you have the notes. Now we will, of course, during class present supplementary notes, but for the most part during class we will devote our time to analyzing chemical systems, so that you come to grips with understanding the chemistry that is occurring in the system. What do you think the most common system is that chemists study? Most common system that chemists study. What?
Water.
That's not a system, that's a substance.
The atmosphere?
Nope. In laboratories, what do you think chemists do more than anything else? What do they run? What do they conduct? Reactions! That's right. Processes by which we convert materials called reactants to materials called products. Processes by which we can make materials which we need. Processes by which we make new materials. Materials whose properties may not yet be understood. Obviously not if they're new materials, but which may prove to be very important. There are two ways to study reaction progress. Did you learn about these two ways in Chemistry 2045? I bet you did, but likely it wasn't pointed out in quite such an explicit fashion. The two ways by which chemists study reaction progress is by thermodynamics and kinetics. That's right. And for the most part, in the first year, we devote our attention to thermodynamic-based investigations, because kinetic-based investigations oftentimes involve theories and mathematical considerations which are beyond the scope of what we can do in the first year. And from a practical experimental standpoint, kinetic investigations oftentimes involve gadgetry which we cannot possibly afford to make available for your use in the first year laboratory. Very expensive, fancy gadgetry. And then we'd have to spend a lot of time to show you how to use it. Then we'd have to spend a lot of time to show you what the data meant that you collected by such investigations. And this in and of itself takes years. Obviously not achievable then in the first year. So again, for the most part, and in our case, for this gathering exclusively, all our studies of chemistry will be founded in thermodynamics, where what we really do will be to study the properties, stability, energy, structure of products, compare them to the property, stability, energy, structure of reactants, and see what changes took place in properties, energy, stability, structure as reactants converted to products, which will allow us to understand why, from a thermodynamic standpoint, the reaction proceeded or did not proceed in accord with the equation for the reaction which we wrote. Now let's get at this in a more practical fashion by starting to take a detailed look at the first thermodynamic consideration, which we look at in Chemistry 2046. Equilibrium, which we pointed out the other day. Extremely important thermodynamic condition, arguably the most important thermodynamic condition, because the equilibrium condition is the most stable thermodynamic state in which a reaction system can exist. Which means practically just about every reaction under appropriate conditions will achieve this condition. And at the equilibrium position, no more reaction progress is made, which means we need to know how to understand equilibrium, we need to know how to determine equilibrium, and we need to know how to control it.
Do combustion reactions have an equilibrium?
Sure. But the equilibrium constant for a combustion reaction is often a value which is enormously huge, which means practically most combustion reactions are one-way streets. The question was asked about combustion reactions. Do they establish equilibrium? A good question. What is a combustion reaction? Since the question was asked. That's a good question. I'll talk about it for a moment. What's a combustion reaction? How would you look at an equation for a reaction and identify it as a combustion reaction? What is that? Yeah, look for oxygen as a reactant. Practically speaking, that's the way combustion reactions are defined. Now, if you take a hydrocarbon, gasoline, or the simplest hydrocarbon, methane, which is CH4 formula-wise, blah, 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 and write the equation for the reaction of the hydrocarbon with oxygen to make under perfect conditions carbon dioxide and water, you'll find that you have an equilibrium constant which is enormously huge, and you'll find that you have a reaction which is driven by both thermodynamic factors, which relate to what we need to know about a reaction from a thermodynamic standpoint. Is it or is it not spontaneous? Can it or can it not go from a thermodynamic standpoint under the conditions under which the reaction is being observed? And unfortunately, in 2045, most 2045 classes and 2045 textbooks devote their time to only studying one part of thermodynamics, which is stupid. Because you can't answer the important question, is the reaction system spontaneous? By just studying change in enthalpy. You did this, didn't you, in 2045? Delta H. But in 2045, you didn't study delta S, did you? That's terrible. Because without delta S, change in entropy, you cannot know if the reaction in question is spontaneous. So we won't leave that out in our studies. But for now, bear in mind, as we said, most combustion reactions have very large K values. That means they're practically speaking one-way streets. You needn't try to hurry up and write that down. But is this a combustion reaction? Does it show the combination of a material with oxygen? Yes. So it's a combustion reaction. It corresponds to the combustion of nitrogen with oxygen to make product nitric oxide. What do you think about this as a go? You think this goes? You think this goes readily? What evidence do you have to support the conclusion that this does not go readily? Our atmosphere is rich in nitrogen, isn't it? And fortunate for us, it's also quite rich in oxygen. If this reaction went readily, would there be oxygen in the atmosphere? No. Would we be here? No. How about that? So there's an example of a combustion reaction which, practically speaking, is a no-go. Got any idea why this is a no-go? Triple bond in nitrogen. That's it. Because for this thing to go, you got to tear apart nitrogen molecules. And nitrogen molecules are preserved by the third strongest known covalent bond in the realm of chemistry. There are only two other bonds known which are stronger than that, which preserve the structural integrity of the N2 molecule. We'll be talking about those later on in the term. The second strongest bond is that which is shown by the triple bond in the carbon monoxide molecule, CO. And the strongest number one triple bond is in the NO plus ion. But never mind that for now. Okay? I just put that up to show you that all combustion reactions are not goes. The K value for that is very small. Because practically speaking, it's no-go, at least not under normal laboratory conditions. Fortunate for us. Because if it was, as we said, we wouldn't even be here talking about this. All right, back to chapter 17. First, I ask you to fix a blunder. At the bottom of page 1 of chapter 17, you'll see an equilibrium constant expression for the hypothetical reaction involving materials A, B, and C, which is written upside down. Turn that equilibrium constant expression over, so to speak. Invert it to make it correct. I didn't catch this when I proofed these notes, which were published 4 years ago. I need to update the notes. A lot of what we do in class will be in reference to the updated version of the notes, which you won't see in the notes, but you'll find in class. All right. Comments. As we mentioned yesterday, equilibrium is established in a dynamic system, which means a gas phase or liquid phase system. When the molar concentration of solutes, square bracket is notation for molar concentration. You learned this in 2045 laboratory. At least I hope you did. The dissolved components of a liquid system, the solutes, and partial pressure of gases in the system are non-zero and constant. Consider water solid in equilibrium with water liquid. As you know, this condition is established at 0 centigrade, 1 atmosphere pressure. As a consequence of the fact that for this system the rate of melting is equal to the rate of freezing. Or water liquid in equilibrium with water vapor. This condition can be established at a whole bunch of different temperature and pressure combinations over the general temperature range of 0 centigrade to 100 centigrade. For this system, the rate of evaporation is counterbalanced by rate of condensation. These rates are equal. We talked about that one yesterday. K, the equilibrium constant expression, is written for an equilibrium system to show the ratio of the molar concentrations of products multiplied times each other. You'll see this when we write some equilibrium constant expressions. As well as the partial pressure of gas products. They're all in the numerator of our equilibrium constant expression. Divided by. That is to say, the components of the equilibrium constant expression which you find in the denominator of the expression. Molar concentration of reactants times molar concentration of reactants, however many reactants we have, as well as times the partial pressure of gas phase reactants. Now we can also express concentrations for gases as opposed to partial pressures. But it's more convenient to refer to gases which are part of an equilibrium system in terms of their partial pressures. We'll talk more about that in a moment when we return to this system, which we talked about in brief on Wednesday, and we'll talk further about it today. Reminder, the square brackets are notation for molar concentration. P simply means partial pressure. You learned about partial pressures of gases when you talked about Dalton's law of partial pressures when you studied gases and gas behavior in Chemistry 2045. What reaction system components are not found in the K expression, even though they're part of the reaction system? Solids, because concentrations of solids are fixed. Doesn't make any difference how much you got. Bigger piece of chalk, littler piece of chalk. Calcium carbonate principally. But the concentration of calcium carbonate in each piece is the same. Here I have more material. Concentration is the same, calcium carbonate. Or solvent. Solvent, practically speaking, is a pure liquid. You'll find some comments in the notes that for a pure solid or a pure liquid, and we take a solvent to be a pure liquid, even though these may be part of an equilibrium system, from a number standpoint, they are not contained in an equilibrium constant expression because, rigorously speaking, we don't use molar concentrations or partial pressures for equilibrium system components when we write K. We use activities. Now we're not going to do anything with activities because we don't have the wherewithal to study activities in the laboratory. But by definition, the activity for a pure solid is 1. And the activity for a pure liquid, again we take a solvent to be a pure liquid, is 1. Well then, since it doesn't matter how much you got, the activity always being 1, you put 1 in an expression, that changes nothing numerically. So we realize an equilibrium constant expression contains or is composed of molar concentrations and or partial pressures. Maybe I should put a plural in here. For system components which undergo a change as equilibrium is established. Well, we've already seen. For a pure substance like a solid, little piece, ton, who cares? Concentration is the same. And the numerical value for the equilibrium constant. Is at a particular temperature an unchanging value. That's why it's called a constant. Now we'll see an exception or two to this statement, but not be concerned with that until we get to it. Bear in mind that practically speaking, you only change the numerical value for an equilibrium constant for an equilibrium system if you subject the system to a change in temperature. Now, back to these two equilibrium systems, A and B. Directive number 1. write the equilibrium constant expression for A and B, given that the thermodynamic convention for reference to gases, if they're part of an equilibrium system, is in terms of partial pressure. Right now, on your paper, let's do it. These are the systems A and B. Clue or hint to write the equilibrium constant. For A, you'll have to remember what I just mentioned to you a moment or so ago. What's it equal to? I heard it. 1. Ah, that's it. Wonderful. Now let's look at B. Pure water liquid in equilibrium with vapor phase water. We talked about this on Wednesday where we had the unstoppered flask and the stoppered flask. Now I've got stoppers in both flasks. And each flask still contains the same water which we had placed in the flask on Wednesday. So in each flask right now, equilibrium B exists. How will you write the equilibrium constant expression? You can write it two ways. One way is better, but both are acceptable. If I take this flask and I apply enough pressure to the stopper, the rubber stopper, so as to force the stopper deeper into the cylinder, will I change the molar concentration of gas in here? Water vapor? I have to. I'm making the volume which it occupies smaller. But I will not have changed the amount of gas that's in the vapor phase. So, I can do this. But the better way to do it is this. Now, from a practical standpoint, let's see if you can recognize why this is the better way to write this K. What I'm asking really is, if I now assign you the task of evaluating K, how eval K for system B? Do you realize that if you want to do this, molar concentration, at the minimum, you've got to make some volume measurements, don't you? You've got to find the volume of the vapor phase of this system. Now, I have a feeling you'd be clever enough to figure out how to do that if I set you free in the laboratory to do that. But if I choose to express this equilibrium constant in terms of this, then I don't have to fool around with this volume measurement. How would I get this? You talked about this stuff in Chemistry 2045 when you talked about gas behavior. At least I hope you did. What's this? Something which maybe you don't see much of anymore. If I had my way, this is what you'd use in the laboratory to measure temperatures. There's nothing wrong with learning how to read a thermometer, as opposed to sticking a piece of metal in a solution and having a computer spit up the temperature, from which you learn nothing. I argue this with my colleagues. You computerize everything, and you're taking away learning from these students. They know how to use computers. They don't know chemistry. So when you put the chemistry they're doing in terms of computers, guess what they're learning? Nothing. You need to learn how to make measurements and understand what the result of the measurement means. With this device, a thermometer, what measurement would you make to evaluate P gas? Water gas. We'll give you an idea. I'm measuring the temperature of the water liquid that's in the flask. I've got a value of, looks like 23.1 centigrade. 23.1 centigrade. Okay? If we have now determined by measurement at T H2OL equals 23.1 centigrade. What would you do now? I'll give you a hint. Nope, I can't give you that hint. We're not doing that experiment anymore. Pardon me. So I'll give you a directive rather than a hint. You've got the notes. I want you to open the notes to chapter 21. In a moment I'll tell you the page. 21.5. Open the notes to page 21.5. You'll see a table on that page, table 21.1. You looking at the table? As you look at the table, tell me the answer. What's the K value? Louder, I can't hear.
20, around 20.
What is that?
Around 20.
I want units.
Torrs.
Torr. How about in atmospheres? Does this table also give the information in atmospheres?
Isn't it like 600 torrs for an atmosphere?
760 torrs in atmosphere. I don't remember if the table also gives pressure values in atmosphere. Just torr? Torr's okay. Right? Because we recognized the equilibrium between water liquid and water vapor exists when we have a condition of humidity known as 100%. Which means the tendency for water liquid to evaporate is counterbalanced by the tendency for water liquid to condense. Which means the vapor pressure for water liquid at this temperature, which measures its tendency to evaporate. Did you learn that in 2045? Vapor pressure of a liquid or solid is a measure of the tendency of that liquid or solid to evaporate at the temperature at which the substance is observed to be. And at this temperature, you've told me that the vapor pressure of water liquid is on the order of 24 torr. Is that correct? Which means the partial pressure of water vapor has got to be 24 torr, because that's the only way that equilibrium can exist. If the temperature, or if the tendency to evaporate, which is the vapor pressure for water liquid, is exactly counterbalanced by the tendency to condense, which is measured by the partial pressure of water vapor. Did you learn that in 2045? Well, if not, you learned it now. Now, let's take a brief peek in the couple minutes we got left to look at these systems, which we'll look at in greater detail on Monday. 1 molar calcium chloride solution, 1 molar hydrochloric acid solution, 1 molar acetic acid solution, and saturated calcium carbonate solution. Of these 4 systems, 2 of them have an equilibrium which exists involving solute. Here's the solute, here's the solute, here's the solute, here's the solute. I want you to identify the 2 systems of these 4 which contain an equilibrium that involves solute. And then I want you to write K for the system, because you've recognized that for that system equilibrium exists involving solute. And finally, the last and most important directive for today, and practically speaking for the whole daggone term, is to realize if you're going to do any chemistry on a system, here's the 4 systems that we're presently considering. The 1 molar calcium chloride solution, etc. If you're going to do any chemistry on a system and understand this chemistry, watch out, here comes a really brilliant, challenging, hard to understand statement. You have to know what the system contains. Wow! I want to know when general chemistry textbooks are going to figure this out, because not a damn one of them has yet figured this out. Isn't that terrible? Not a one of them has figured this out. Not a once has a general chemistry textbook yet been written which challenges you to figure out what the heck's in a system. And when you figure out what's in the system, you express this in terms of principal system inventory. Do you have any recollection of writing principal system inventories? Did you do this in 2045 lab? Starting with assignment 4? Do you think when you did that in 2045 lab, I was laying foundation for you to understand what the heck's going on right now? You betcha. We'll pick it up from that point. And if you need to go back and read the 2045 lab stuff on this, do it.